Welcome everyone to the June edition of the Hamilton Meetup. This meetup will hopefully be done in about 60 minutes or less. The rough agenda is basically we're going to go over some news or new features that we've kind of added into Hamilton. I will demonstrate or demo a few brief snippets of this, and then otherwise the deep dive will be on how do you use, or how can you think about using Hamilton in a RAG context. So I'll explain a little bit about RAG, kind of how it works, and then specifically where to conceptually think about where Hamilton could be a good fit if you're trying to do that. And then otherwise we'll have time at the end for anyone who wants to kind of share anything or talk about something. But otherwise, since we're a small group, feel free to interrupt, slow me down, and questions are always welcome. So in terms of the news,
sorry for interrupting. We hear your kids. If you want to put it in directional mode for your microphone.
Is that better? I don't know. You're right. The directional mode on my microphone was not switched. Cool. So we have released a few things since the last meetup. Quite a number of things. So this is just a highlight of them. So I'm just going to walk you through each one of these features. So just to give you a bit of a sense of what they are and kind of how you can use them. So the first one is we kind of revamped and added and iterated on the IPython magic that one can. So if you develop in a notebook and you want to do something with Hamilton, we have, Thierry has done a bunch of work to make this experience even better. So in short, so I have a Google Colab notebook here that I'm just going to briefly run through just some of the high-level things just to remind you what this feature is and how you can kind of use it. So to use it, you basically first need to import Hamilton. And actually, I think, I need to actually do one more thing here, which is actually install Hamilton. Hamilton. As you can see here, Hamilton's not installed. The one thing you do and we have to do first is install it. For those who don't know what a Jupyter magic is, effectively, if you see percentage signs in a cell or a notebook, they're basically what we call magics. Single percentages mean line magics, meaning the magic extends. It's kind of like a command line. But ones that start with double percentages are effectively mean that the entire cell is kind of used for the magic. You might have seen kind of examples with time it, which is essentially just time this function. But you'll see that for Hamilton, we have added a cell magic that enables you to kind of think of a cell as a Python module that in Hamilton knows something about. So if I rerun this, the extension should download since we've kind of installed it. And so if you are ever curious about what you can do, if you do a question mark in front, you can always kind of get the documentation out. In the case of running a Colab, we'll actually open up a little sidebar where you can kind of see the inputs and arguments that you can pass into cell to module. So in terms of just the high-level basics, you define a cell that effectively maps to some sort of module. Here, we're defining a module called joke, and we have a single function. D, as you can kind of see on the shorthand on this side, is for display. Kind of close that. So you can kind of see the idea is as you're typing Hamilton, you can kind of see your pipeline come to life as you're kind of typing more. These functions get put into the namespace of the notebook, so you can just simply kind of refer to them via the module or just via the function directly. So that way you can easily iterate and create functions, push them into the module, and then continue and have access. There is various. So some of the new things that we added is the ability to actually change the kind of display configuration. So you can now, as an argument to display, pass in some configuration that will actually change how things are displayed. So for example, by default, it shows things left to right. But if you wanted to change the orientation, you just got to pass in something and you'll get a different picture. Another new feature that we added was the ability to write to a module. So usually in the development process, you're starting at a notebook. Maybe you don't want to check that in and run it, in which case you can then easily write the contents of this module out to write the contents of the cell out to a module just by specifying the write to file parameter. It will by default then create a file called joke.py that then you can then import or at least check in into your Git system. And otherwise, let's see, any other new features? Oh yeah, and so the other new features is that you can actually pass in a builder. This means that you can actually do a few more complex things, but suffice, I'm not going to dive into it here. But the point is, you can actually now have, when this runs, actually also then begin to execute the code with some inputs and outputs. So if you want to iterate, that way you now can do so in a notebook. Otherwise, just to, and so the benefit of adding in a builder is you can actually also add in a bunch of different other adapters. And so here I'm creating a builder with the print line adapter. I am now passing in a builder, asking it to display, but I'm also asking it to kind of execute everything. And so when I run this, you can see that we get some extra prints out from the print line. Anyway, so in short, great setting new features. Would love feedback if you have it. Otherwise, any questions here from anyone?
I'll just raise my hand and say it's cool because this also allows you to track the notebook execution with the Hamilton UI. So here, like the adapter that we gave is a print line, but you could have the Hamilton tracker for the UI. We even have a PDB debugger, so you can debug node by node. Sometimes like the notebook interfaces, like whether it's like Jupyter Lab or VS Code, they're not great for debugging, but you can have a debugger node by node with this.
Cool.
Also, I want to add that Stefan and Thierry wrote about this instead of the process of building one. I'm going to send the blog post over. This was on Towards Data Science, and we've written a few times about these things. So if you're looking to create your own one, this is actually a really good resource to understand how they work at sort of a lower level. So both for Hamilton and how you can sort of use Jupyter Notebooks on your own with Jupyter Magic.
There's a fuller tutorial on YouTube on our YouTube channel if you're interested.
I would personally love to see an example of debugging. The PDB PD debugger, I had some difficulties with it, and if you have some, like a workflow that you use, that would be great. Yeah.
Okay, I can put that on my list of to-dos for a video or maybe a blog that we could.
Sure. Cool. Cool. One of the other features we did just to highlight in the last couple of months is the ability to, rather than, so if you're familiar with materializers that help you kind of load and save data, you can now pass them in as part of the builder. Then you don't need to use the different .materialize syntax to execute something. Instead, you can kind of just use .execute. I'll send these slides out, but like effectively, if you want to kind of understand we've added to the doc, so hopefully it's self-sufficient enough so you can kind of understand how to use this new feature. Yeah. So another new feature we released is kind of GracefulErrorAdapter. So usually by default, Hamilton, when it counters an error, it fails and everything kind of stops. Here with this kind of adapter, we allow computation to proceed, and so at the output you'll get the things that you want, except there might be some none or null value that you've kind of set up. So to kind of explain that, here I have some code where we have some functions. It's very simple and kind of dumb dag, but effectively never reached depends on won't proceed because that's how Hamilton works. When this function runs, it raises an error, but we actually want, never reach to kind of to effectively kind of be exercised. So we're not catching errors in our code. We're instead checking output values. With the GracefulErrorAdapter, all we need to do is in the builder, specify this adapter, specify an error to catch, and then some sentinel value that will then be output in place of any values that we expect as output. And so when we do .execute and we ask for will proceed, the output of will proceed and never reached, because never reached, the inputs, the preceding function call to that raises an error. We'll just return the sentinel value. So rather than you having try and catch statements in your execute to kind of handle this, instead you now can inspect kind of the values of .execute.
So yeah, so this is pretty cool because it allows you to sort of just keep going if something fails. So graceful failure is like, I'm not sure if that's like the best name for it now that I think about it, because I came up with that name. Really, it's a like proceed in these cases, which allows you to like explore a few different sort of places in the DAG as opposed to the standard way where it'll fail and the first failure will trigger failure with everything. The implementation of this is also very simple if you're curious, so you can just you can link to the code.
Can I ask something about this, or do we want to continue?
Yeah.
So if I understand correctly, it will return, instead of like, if we don't use this adapter, then we won't get the results, the driver results.
Correct, because an error will be thrown, execution will stop, and then .execute won't complete. Instead, you'll have the do not proceed error being thrown.
And when we use it, so we get all the sub DAGs, or like the paths in the DAG that can be completed.
Yeah, correct.
Oh, that's really cool.
Yeah,
that's really good.
Yeah, I guess to highlight the trade-off is like, if you are building a machine learning model and you don't use this adapter, it will allow you to catch the bug faster potentially, because it will just stop, let's say, after the second node, and you'll see, okay, I won't be able to complete the whole path I wanted. I want to have an error I can debug. But if you are doing, I don't know, you're training 10 model in your pipeline, and you want to retrieve the 5 model that succeeded, and if it fails for the others, you'll say, okay, I'll take the 5 that worked, I'll debug later, and I'll figure it out.
And currently, I think it doesn't have extra metadata on exactly how it failed, because you catch a specific exception. But one thing we want to do is add like a little tracker to it that says like, okay, here are the exceptions. You can start pointing to that, and then you can expect it. Later, that would be a pretty simple thing to add. So if you're interested, let us know.
Cool, good question. And one of the highlights, I guess, of the last couple of months, we released Hamilton a pip install, a UI. Initially, it was just you had to use Docker, but now in the last week, we've also made it pip installable. The key features is, if you're running Hamilton, this would be kind of useful for the RAG and kind of document processing side, is you can actually then visualize, version, catalog, and kind of understand execution telemetry about kind of this Hamilton execution. So just to give a quick demo of that, I am going to jump to the UI. So when you can organize your Hamilton kind of DAGs into projects, when you kind of click into it, we try to give you at least information on how to get started. So how do you log information to it? But otherwise, just to give you an example of some of the features. So if you're doing stuff in a notebook, or you've checked it in, part of the idea is that if you, as this kind of, if you add this one line, this adapter to the adapter's argument, you'll get all these features for free is the main point. So one is around versioning, so we can actually tightly version, understand what's changed about your code and to kind of shape your graph. We can catalog everything that we've seen. So in terms of, in case of a machine learning example, it could be feature transforms, model fit functions to what actual models were output, or data sets were input. And then more importantly, I guess, is that Hamilton's very visual. And so in which case you then have an interactive visualization that you can kind of more easily introspect and understand what your code is. You can see the code via side panel view. You can kind of see what's color coded as to what's upstream and downstream or something. And then if we can also, there's some ways to kind of other ways to visualize or collapse or display the graph. And so in which case here you can kind of see, we can actually walk through the code and understand what's before and after it. So you can more easily kind of understand a process or explain it to someone end to end. We also capture the code. So if you want to kind of look at it, and then on the telemetry side, when something runs, we can actually track it. And so in the case of, say, a failure, the idea is rather than you going through a log, we can you have a lot of instrumentation that comes for free, so we can actually pinpoint and tell you, hey, look, this is where your code failed. We can actually then see the stack trace. We actually capture the code, and then if you want to kind of compare it to some sort of prior run, you can do so. And so in which case, the reason why this code failed here is because there's an error, and we can kind of discern that. But in the case where it was not a code issue, the idea is that we can actually help you walk you through the different paths to that point to understand, was it code or data. And so by default, if you have things that are in memory, like pandas or polars data frames, the tracker will take summary statistics and track them for you. So then you can easily more compare and understand kind of what went on and what was different with respect to the different executions if you have to go ahead and debug something or understand if something's changed. Yeah, let's see. So that was the UI. It's pip installable. So I'm not gonna. I was gonna do a live demo, but I guess in terms of time, it probably pays to move on a little. But otherwise, you can be up and running in 5 minutes with since it's now pip installable.
Yeah. Meaning you just do pip install Hamilton bracket whatever, and then Hamilton space UI, and it should just run. On Windows, there's a slightly different incantation due to Django issues, but.
I have a question, small question. Yeah. I just don't remember. I think we talked about it, but can I see my DAG like before I execute it, or like, can I?
Yeah. So when you when you do this, a version of the graph is logged. So after you add the tracker to your driver and you build a driver, you've instantiated a graph. In which case, you can then come here into the versions and kind of see, click it, and then pan around with it. You won't have any execution telemetry or stuff around it, but you will at least be able to kind of come in and kind of see what the shape is.
Great.
The way it works is it logs like a template almost, which is the shape of it, and then it kind of fills it in as it runs when it's executing. So even if you don't run it, if you just create it, you can use that to log it, and then it'll capture version information and point to your code.
All right, let's see. The other another cool feature released thanks to Thierry was for those of you who know what the Kedra is. So this is only relevant if you know what Kedra is. We now have Hamilton can actually run Kedra projects. So here I'm just showing we now have a plugin under plugins Kedra that can convert a Kedra pipeline into a Hamilton driver that then you can kind of run and execute. The point here being that if you pair it with the Hamilton tracker, you now can run your Kedra pipelines, and as it executes, have it log in a way that you can kind of see this visualization, and then also similarly see profile information for node runs as well as summary statistics. So cool feature. So if you use Kedra, great way to plug in and kind of just make use of the Hamilton UI. And then just the other week, we also added support for MLflow. So MLflow, for those you don't know, is an open source project out of shepherded by DataBricks. But effectively, if you think of Experiment Manager or something where you're tracking F1 scores and model metrics, it is a place where you can kind of store that information. It also is a place that you can store artifacts, so meaning a saved model, for example. We've added support for being able to load from and write to MLflow, since you can use it as this kind of artifact store. But in terms of what I think is cooler is that we have a Hamilton tracker that you can kind of add to your Hamilton DAG that then will auto-populate a lot of the information that into MLflow that you otherwise would have to manually go ahead and curate yourself. The cool part about this is that you don't, in your code, you don't have to actually import MLflow at all in terms of your logic. So there's a notebook here. I guess links and slides will be posted, so you can kind of go play around with yourself. The main salient point is that in this machine learning code here, there is no MLflow import. If we want to then track a lot, we just need to I'll track a lot of this by default to MLflow, to some MLflow kind of experiment project. We just need to instantiate the tracker. It takes in a bunch of optional arguments and things, so you can customize it to point to MLflow to however you kind of run MLflow. But the idea is then when this runs, it's you specify kind of the outputs that you want, and those outputs then will be logged as artifacts to MLflow if it's a known type that we know about. So plots, figures, and kind of models. So typical one-line way to kind of integrate MLflow. The way we see Hamilton UI and MLflow kind of integrating is that MLflow being more of a repository of things, and Hamilton UI being more around kind of execution and finer grained detail. We're obviously looking to better integrate the two together, but right now, since you can add multiple adapters to a Hamilton driver, you can actually add both in and get the best of both worlds for now. Thierry, did I miss anything?
No, I guess the only thing that you see exactly here, MLflow has the concept of an experiment and a run. So the experiment is like a group of runs, and a run is a single execution, and you can even have nested runs in that case. And Hamilton has the concept of a project, and then a DAG that has a DAG name, and then DAG runs. So there's a similarity between the two. Right now, like in this example, I suggest like having the same project ID passed to the two and the same DAG name used as a run name afterwards in MLflow. But we could try to make that a bit more seamless for you in the future.
Cool. Awesome. Gilad, no questions? Awesome. Right, so that's kind of what I showed. All right. So anyone have any questions about that? Else, I was going to switch tack and start talking about, explain a little bit about RAG and document processing.
I do have a question. I'm just not sure if it's for now. I think I asked Thierry this already. I'm just curious if it's possible to log a DAG as a model in MLflow. Like, yeah, the whole DAG, not just the artifact of the model.
I think so. There is, it does log the JSON representation. So it does have all code and nodes and stuff, but the hard part is deserializing. There's no deserialization component to that yet.
Yeah, I can take that offline afterwards, but essentially MLflow is a feature that they call like PyFunc, like Python function, and you can log basically anything that's a class or a function and use it for prediction, but we would need to add code for that, and then it would just pickle the whole Hamilton driver and unpickle it.
And pickling that type of stuff can be a little difficult.
Yeah.
Just because you end up with like module pointers and you don't know what's included as a thing inside your pickle and outside. So, but that said, you can always like hack around pickle and add your own, imagining that your own custom pickle methods.
That's where like MLflow is strong versus if we were to build it ourselves. Is MLflow is already figuring out all the dependencies of the currently instantiated code, and we'll put that in a conda file and the requirements txt, and like it will automatically get that metadata and put it in near the artifact that we want to create.
I think from what I know from a similar Kedro project is that you don't necessarily have to pickle your code or driver, but maybe I can help with that.
Yeah, sure.
Okay, cool.
Yeah, cool. I mean, I think there's a few options. We'll take that on, take it up offline. Cool. So the agenda, for this deep dive is to go over kind of three things. So the components of a RAG system. So independent on Hamilton, what is RAG? How does it work? Got to show you some code. So this is going to be showing how you can use Hamilton to apply for this particular use case. And then caveats. So then what's good for, quick demo, but then say you really want to take this to production, what are we going to kind of do? So effectively, you want to leave you with a high level mental model of the process, some code to help you get started, and then if you do go to production, what are the things that you're probably going to have to think about and worry about for your particular context. And this will be, a lot. I think in the next 30 minutes, like since we started, I think a little earlier than so on time, I will slow down and not try to rush quite so much. But otherwise, if you do have questions, do feel free to stop me and slow me down. So, what is retrieval augmented generation, or RAG? In general, the big picture is you have some sort of prompt or context that you want to feed to some LLM to get a response, right? Retrieval is augmented is really just you're really trying to figure out what to pass into this context to augment the generation to get the response that you want. And so the purpose, therefore, a RAG is to, again, so figure out, okay, of all the things that I could put into this particular context for a prompt to pass to an LLM, how do I do that? What should I fill into the available space that you can kind of pass to it? From a systems level, I kind of see the process of a RAG system in the following kind of way, right? You have some sort of knowledge base. This could be PDFs, this could be documents, this could be websites, this could be Notion, images, etc. You have some internal knowledge store. You then have to process that knowledge store into documents or something that for RAG in particular, you have vector stores. You basically need to create, you need to extract the text, extract embeddings and other metadata. You then need to put it into some sort of store that you can query, so that if you're trying to build some sort of application, say a chatbot or something, when a question comes in, you can figure out how to build a query. It will then query this kind of index data set that then will pull out and retrieve the right context so that you can feed it to an LLM to get the response that you want. Any questions? Now, there is some, in terms of pre-processing documents in the query, there is some shared logic here in terms of how it works. Not so just dotted line relationship, but otherwise in terms of today, in terms of how Hamilton fits, Hamilton has fits really well in terms of taking these documents or some sort of document store, helping you pre-process that, and then write logic in a way that you can also then share for it from the query side perspective. So I like to think of, zooming in into kind of pre-processed documents, how I like to think about it is that it's 5 steps. First is you got to load data, you got to extract it, you again got to chunk the text into subsections, and then you're going to create some text embeddings, and then you're going to store it. I'm going to walk through each of these sections to try to ground and also give you a mental picture of what they are. So you get a document, right? We then, out of this document, say it's a newspaper, we want to, extract, the text of the relevant portions. We then want to chunk that up. We don't, so things might be in paragraphs. So maybe it makes sense to kind of split on paragraphs, or maybe there's some really large paragraphs. So maybe they talk about multiple things. You got to figure out how you want to, divide this text. And then from each of them, that's where you then create some sort of embedding. So a vector, which is a semantic representation of that text. Now, this is a call out, right? It could be to an API endpoint, or if you're hosting models locally, say from Hugging Face, a transformer model or something that, given text, creates some embeddings, some vectors. You're then gonna store all of this information in some sort of vector store, so then you can query for it, retrieve it, and find things for later. The mental note is that given a document, it can create one or more embeddings. So you can kind of think of, given some input, you're going to have an explosion potentially of text chunks and embeddings, and this is going to vary and be different depending on your particular context. So Slack messages are nice and short, probably one-to-one, but PDF documents probably going to have a lot of different potential vector embeddings given one document that you kind of process. So just to ground that, say we want to process Hamilton's documentation. The first thing we got to do is we got to load it, right? And so this page is HTML, right? And so we could then, to get access to it, we need to kind of load it up and get access to it. And so the load step, this will be different for each of your contexts. So this would be open a file, go to some website, maybe if you have your own proprietary format, somehow read that in. right? Now, so then the extract phase is given now that you have access to the internals or of this document, you then have to extract things from it. So, for example, for RAG or for the purpose of this knowledge base, like we're not actually too interested in the left-hand side of this. Instead, we want to get the content. And so the point of extract is to just extract the things that are relevant for your particular process. And so what you do here is very context dependent. In terms of what to extract, how to extract, right? It can span the spectrum of very simple, so some rule-based stuff. Maybe it's some regular expression because you know that given this page structure, all the content is always in some div tag that's named something specific. In the case of PDS or something where it's an image, you might have to use object character recognition. So given an image, try to pull out the text from it. And then there are now more of these multimodal models that then you can apply, just give it something and it will figure out, what to extract and kind of embed. So lots to play around with here. And then what you do here, it will be, different from one particular context or company to the next. The next is then we now have to chunk it. So given that we extracted this text, we now need to extract the relevant portions, right? And so here, I probably don't want to, if you think about the ultimate end goal of this chunking is that these chunks are going to be fed in potentially as context to the LLM, right? And so if you think of things in that way, then that's kind of, and you work backwards, that's kind of the strategy approach to think about chunking. So we don't necessarily want to pass this entire front page to the LLM. Instead, we want to chunk it into the relevant, say, portion. And it just so happens that by paragraph, it's talking about something different, in which case it makes sense logically to kind of have them as very separate chunks. So again, depending on your context and use case, you'll choose a segmentation or chunking strategy that makes sense. In terms of decisions to make is how big these chunks are. Do these chunks have overlap? Since you can actually say you have some long text, but really it's got some relevant things where it makes sense to kind of overlap. You can kind of there are various sorts of strategies there where that may or may not make sense. But otherwise, go ahead, Thierry.
Okay. So yeah, I didn't want to interrupt. Could have finished your sentence.
Sure.
One thing that, like, just from experience, that's important when you're working with RAG. Note that, like, the size of the context that you will give your model will influence largely the size of the response that you'll get. So if you have very large chunks and you give it 10 chunks, you will have an enormous answer by the LLM. This also eats your API credits. So it's an important decision to make how big you chunk, because you will then want some level of diversity in the context that you give the LLM, and so there's a lot of implications. So you should iterate over the size of
I was going to say, you can obviously make the LLM say, be concise, but obviously that's also dependent on what it put, the size of the input that you kind of put in that Thierry said. So then from chunking, we can now move to embedding, right? And so given a document, we have extracted the text and then we've chunked it into the sections that we want. We now can then create some sort of vector embedding, which is a semantic representation of that text. This is the point of this vector, is that this is what, say, if you're using a vector store, uses to find or help you find similar text. So given some text input that you can convert to a vector, you can then now use linear algebra or other various distance measures between vectors to identify and find things that are similar, such that you can then pull out the representative text and push it to it will pass it in this context to LLM. There are many implementations of vector embeddings, as I kind of mentioned before. So you can use, say, OpenAI has a bunch. There's Hugging Face transform models you can run yourself locally. So there's a decision as to which embedding to use. So depending on your domain, some might be better than others. Something that you have to kind of understand a bit more about what those vector embeddings were built on to kind of make a decision there. Otherwise, the vector length, there are different implementations. So a larger length of vector generally means it's more discriminant, and you can discern more things, but at the cost of having to store more data. And then depending on what you choose, you can also just mention here that here's another context where you can do fine tuning. So fine tuning generally means on the output of an LM, but you can actually also fine tune embeddings. So given some embeddings, you can actually make do some, what effectively is doing some linear algebra to make something that is close together, further apart. So you can, tell the difference between them more easily. So just to mention here, I'm not going to dive into it, but here's another context where fine tuning is applicable, or the concept of fine tuning. And so lastly, now with so given the document, we've chunked it, we've parsed it, we now got embeddings, we now want to store everything. And so point here is this, you want to store the information that's going to help you then retrieve it and pass to the LM. And so effectively, you should be storing the text, the embeddings, and any other associated metadata. Since with metadata, you can actually help you filter or prune potentially things that you look at, since that can improve your retrieval performance. So the main decision here is, where do you store it? Again, there is no right answer here. I think it depends on the size of things, right? So if everything fits in memory, probably don't need a vector store, just flat files, right? But if it gets larger or other things, then there are vector stores. There's various implementations. Are they distributed? Are they open source, etc. So Postgres now has a PG vector, which is an extension that allows you to do more vector stuff. So you can store vectors and the text and metadata in the same place, right? So there's a lot of options. This place is evolving, and so in which case one of the things I would suggest is to ensure that you can easily swap vector store implementations or places where they're stored to make sure that you're not too locked into a particular implementation. Thierry.
Yeah, I think looking at your existing data storage and see if they have new plugins to store vectors, because database used to have like strings, float, booleans, but vectors are now more and more common as a type that they support. Otherwise, like you can always store that in a table, right? Essentially, you have a document ID, you have the text in a column, and then you have a column in your, let's say, a Parquet file or a Pyro file that has a vector. Many like file storage also allow to store vectors.
Any questions on this? I'm now going to jump and try to reground and repeat some of the stuff, but showing through code. So you can also follow along. So let me just in Google Colab if you wanted to.
Question.
Yep.
If I wanted to kind of replace a part here, a section with Burr, kind of with a agentic workflow that needs to make, is it? I'm not sure, how do they talk together, if at all?
Yeah, I mean, so up to you. So usually Burr, for those who don't know, is the Hamilton sister framework. If you get your American history, you'll kind of get the reference a little. The idea with kind of Burr is that where's the next one? Is that you use it for the side of things, for the chatbot side of things, because usually the knowledge base is very can be modeled as a directed acyclic graph. It's very that's a great way to model it. Whereas in this chatbot, there's loops, conditional decisions, and maybe cycles. In which case, Burr, the other framework which is designed to kind of enable that, would be the place where you would typically see people using Burr. If that makes sense, Gil.
So Burr, I would use kind of Hamilton within Burr. Or
yes, you can. Yep, that's one way to look at it.
That said, it can be two separate things where Hamilton takes it and puts the data into the index set, and then Burr is responsible for the querying. And then if you want to use some of the same code, Burr can call out to Hamilton, which is, we actually designed Burr to be kind of a harness for Hamilton, and Hamilton just like pulls data as a pure transform and returns data. So that's like move state to state. But really, you can use them together or not. It depends on how you want to organize your code.
Yeah.
Yeah. Okay. Cool.
So I put a link in Google in the chat. So if you want to follow along in Google Colab, but effectively, I'm just going to be walking through the process to chunk a single Hamilton document, so some documentation from Hamilton. This document, this is kind of self-contained. So if you do not have things installed, go ahead and install it. Otherwise, load the kind of Jupyter Magic extension. Now, this does require OpenAI. So if you do have a key, this is the place to set it. I already have it in my environment, so I'm not going to set it. But effectively, feel free to stop me, slow me down. But effectively, I'm just going to try to ground kind of what I mentioned before, but with code, and then showing how with Hamilton you can kind of do it. So to set up things, I am going to use a bunch of objects that will then kind of contain the information that we want to get at the end of things. We're going to be kind of passing this through our kind of pipeline. So this is one way to model it, not the most exclusive way. Just this is the most simplest way that I found to kind of do it. The point here is I'm kind of creating some objects that will, so I have a concept of a chunk which has an index, so it knows what index of chunk it is from what document, the text, and then embeddings and metadata. And then similarly for a document, I have an ID for it, I have a URL of where I got it from, the raw text, and then the list of chunks that then will map to this object. So to kind of ground, loading, we just want to basically, given some URL for some Hamilton documentation, pull out the text from it. So I'm using, so we're writing two functions here. So we want to get a raw document out, right? So this is kind of what this last line is doing. So it's creating an ID, taking the URL and the raw text. But we also I'm also coupling here extraction. So with extraction, the way that the Hamilton documentation is set up, I know that all the content actually is in between two HTML tags. So I don't need to do anything fancy here. I just have a regular expression that I can kind of use to kind of pull this out. And so I can go kind of test this, right? And so given some sort of URL from the Hamilton documentation, I can call this raw document, rather function to get a raw document out. Now, next up, we then, so in these cells, I'm going to be successfully adding to this kind of Hamilton pipeline. So you can see here, we've created a very simple one. So given a URL, creates a raw document. We now want to, given that text that we've kind of extracted, as you can kind of see here, we want to now chunk it. So I am going to be using LangChain. So LangChain has a kitchen sink of different various things in it. I want to say the best use of LangChain is to use the components that you want out of it, not necessarily buy into all of it. Can talk more about why a little later. But effectively, what I'm going to be using from LangChain is its built-in kind of text splitting and HTML splitting functionality. So just to explain, so given a raw document, we want to then chunk it, right? And so we want to create a document that has chunks with it. So it's going to pull in an HTML chunker and a text chunker, and we can see here that we can actually specify and tweak a few things about chunk overlap and chunk size. So this is a parameter that you can kind of tweak. So the idea with Hamilton, I forget for those who are new, the way that kind of Hamilton works and constructs this pipeline is based on the name of the functions and the function input arguments. So the reason why chunk document has 3 input arrows to it is because we defined a function called chunk document, and it says it depends on raw document, HTML chunker, and text chunker. Hamilton knows to then to resolve HTML chunker and text chunker to be the output of these 2 functions, and raw document being the one the output of this function here. Let's see. So Musa, is that following thus far? I'm not going too fast. I'm gonna pick on you. Sure. So then we can, given some HTML. So if you want to play around and understand what these functions are doing, right? So given a text chunker, it will, or an HTML chunker. In the case of HTML chunker, we could, give it some HTML, and it will, chunk things into, lang chain documents. We then can take those documents and then further split that text. If we want to kind of change, kind of overlap or other things, we can kind of tweak the values of characters that we kind of want, right? Actually, I think this is kind of right. And so then you can play around with this, but just to show you that there are things to kind of play around with. For those who want a better visual representation of what's going on, there is this kind of chunk visualizer that allows you to play around with some of the implementations to give you a sense of, given some text, how is it actually being split. So that's linked in the notebook if you want more details there. And so then we now have created a pipeline. We're given a URL. We create a document. We can then chunk it into chunk the text. We can now then go ahead and try to get embeddings. So I have, I'm going to use OpenAI here. This will implicitly use, the environment variables I set up to get my OpenAI API key. But effectively, given a document, we're just going to iterate through all the chunks that it has. We then are going to get an embedding for it, and then add the embedding to the chunk response and kind of update things there. So our pipeline now looks like the following. So given a URL, given a document, given a way that we can kind of chunk, we create some chunks, and then given those, give it some sort of client, we can then create an embedded document. Just to give you a sense for what these embeddings look like. So given this particular model, right? For this sentence, this is some text that will change into a vector, right? You can see here that we get a bunch of numbers that represent that semantically. And so then lastly, I'm not going to push to a particular vector store just to keep this kind of idea simple, since you can just push to a data frame and kind of store that to a file or something. And so the point of store is to just effectively, given an embedded document and a final thing, convert it into some sort of format or structure that then you can kind of push to or use or utilize then from the inference side of then retrieving information. So so we now have easily completed our document processing pipeline that takes in a single URL, right? Parses it, constructs it, chunks it, embeds it, and then is ready to push to some sort of storage. Now, this is in terms of just explaining this. So what we've effectively set up is a pipeline, but we actually haven't run it all together. And so with the way that kind of Hamilton works, we've been adding the way that this Jupyter Magic works is that we've been adding to a module called doc pipeline. And so to actually then kind of construct this graph, right? We then need to kind of create a driver that then is something that knows about, basically constructs this representation internally. We can then, ask to execute things from it, in which case we want the output of store. And then we output of store, right? So we request store. We then have to provide in the right inputs. So you see here, there's only one input required, and that's because chunk overlap and chunk size have default values. But otherwise, that's kind of the long and short of the simple tutorial of like how to use Hamilton for document processing. And so you can see as a result here, we get a kind of pandas data frame which has which has a representation of this single URL represented in a data frame with the URL, the text, and then the embeddings and various metadata. Questions, thoughts?
No, to me, it's very similar to how you do training and inference pipelines in traditional ML, in the sense that here you have like documents. You can think of it as like the training. You have things stored And then at inference time for your RAG, you need the model to embed the user query and then retrieve from the store the other parts, combine the retrieved information with the original query, then pass that as input to the LLM to then receive text. So there's some shared skills or approaches that you can reuse.
I can also add that I looked at DSPy, if you've seen that, and that really makes training, like it really trains or fits. So I'm just seeing kind of a consolidation of AI, or the world of generative AI, and just traditional machine learning come together. And I'm happy that Hamilton is able to kind of provide for both situations.
Cool.
So yes,
Yeah, we
Stefan,
looked at go ahead, Elijah.
I was gonna ask another question about this. Thierry, you wanna continue?
Yeah, quickly on DSPY, we talked about it internally. We think it's interesting because to us it's more of an offline step, like it optimizes your prompt. But once you have this optimized prompt, or you have the DSPY machinery during the training, you can still use the prompt with like Hamilton or Burr or the other frameworks in place to create pipelines or agents. So yeah, it's definitely an interesting avenue.
Yeah.
Cool. I was going to ask Stefan if you wanted to say, instead of call these in a loop, let's say you want to throw it in parallel and you want to do that all in Hamilton, how might you go about that?
Yeah. So I was just going to say, so this document, I mean, pipeline only runs for one document, but you're going to have like, some way, some means of, a bunch of things, right? And so the simple, you could say basic way as well, you could just, loop over things and just provide the right inputs, right? And so as kind of Elijah was kind of leading the witness, I guess, or me in a way, but effectively the idea is that if you do it this way, this doesn't happen in parallel; it happens serially in sequence. In Hamilton, we do have the ability to parallelize things and help it connect with some means to do parallel processing. And so, in which case, the thing that we kind of want is to take this DAG here and effectively parallelize it, and so with Hamilton we have a construct that we can kind of do that with, and I should just do just to add display. Actually, no, display here. So config. We can. What I've done here is added 2 more functions, and one of them specifies that something can be parallelizable. So here, given we can now, given a list of URLs, we can actually parallelize over each URL is the way to kind of read it. And then we need to then capture or store everything based on the results of that. And so this is kind of what collect does. So we want to parallelize everything and then store all the results of store into a single data frame. And so this is as one way to think about it. It's kind of effectively what we're doing is we're bookending this DAG and saying, hey, everything in between here is we're going to be parallelizing it. And so that's what kind of Hamilton helps you do.
So I think this was like a little subtle what you did, Stefan, but it's super cool. We have a module that we defined above that just runs on one page. Yeah. And then he added a like before and after, which says expand out like map and then reduce back. And by adding the before and after and calling the latest collect one, which sort of does that reduce, you get it all running in a map reduce. So it's a way to take a simple sort of DAG and then run it in parallel over a bunch by just adding 2 functions. It's like really clever. Yeah. And thought of that way of being in Jupyter.
So you can think of this as effectively as replacing the need for a for loop and enabling you to more easily plug in some sort of executor that can parallelize it. So this could be, it could be naively, it could be a synchronous one, but it could be multi-threading. It could be like something like Ray or Dask, which spans out to another system. And so that is, and so we have a blog post on this. So if you want to know more, there's a link here. But effectively, once you Hamilton allows you to prototype something very easily in a notebook, then add some parallelization, then really easy kind of path to kind of scaling.
You want to live try it with the tracker too?
So I mean, oh yeah. So when I already have, I guess, an example in the Hamilton UI, but not for this example. But the idea is that, hey, if you do plug in something, you can kind of see that we can actually track the different kind of parallel executions given something. So if you hook it with the tracker, you can then also see progress where it is and kind of what files it is.
And this can all be run live as you're running your parallelism. So if you're running that, you go over and it takes a while, you can see sort of its progress.
Yeah.
It's pretty straightforward to add an item potency.
Yeah.
So you can say like, oh, like each time it's done, it writes to a file. And then if you have to Control-C your program, the next time you can only launch the ones that haven't been done, and then you can sort of go from there.
Yeah, like so if you added some sort of checkpointing here or here, like you could then kind of skip things you haven't processed. So
I have a question.
Yeah.
First of all, I think it's really cool. I really like it. I mean, but if I were to do this myself, I might have tried to build the code from the beginning to handle lists, or like a list of URL. And this is a different approach. I think it's more elegant in a sense, or easier. I'm just wondering, maybe are there any like benefits of doing it the other way around?
Yeah, so the way so it's a good point. So the way that we set things up, I think, is to make things more unit testable, right? You don't have to think about lists or things. Like each function, therefore, is very atomic. It is very just specific for that one thing. So that is the main difference, is that you don't have to pass in and think about having four loops in each of these functions, or that you would otherwise would do. But like that is the trade-off. But we could actually have made this Hamilton DAG from the beginning, take a list of URLs and then just have lists of things. But because of the way that I think Hamilton helps you think about the problem, is that you can actually then more atomically think about, I just want to process an atomic row at a time and then figure out how to parallelize it.
In the world of like you were mentioning, comparing it to traditional ML, a lot of things you do in traditional ML is like you vectorize it, right? So instead of hitting API requests, you're like saying like, okay, I want to do like 100 at a time. Spark has this like map partitions thing that will do vectorization. So if you're really going to go for efficiency, you'll likely try to find a bulk API and call that in parallel. So you have choices. You can either do like handle all the parallelism inside the functions. Those get more complicated. No parallelism inside the functions, then you'd have to do one at a time and you're handling parallelism. Or some mix where you pass in a bunch of lists, and each of those that could like parallelizable can be a list of lists, which allows you to then hit the like OpenAI bulk endpoint and do that. You can tune the size of it as well. So it's kind of up to you. I think there's good reasons to do either. But the simplicity of having individual API calls is kind of nice.
Yeah, to share my experience here, I think I shared from my own like mistake and challenges. I really suggest sticking to either lists or a single document, like from the start, and only use the parallel collect later on in the process, because otherwise you will try to like over optimize for when you parallelize and collect. But the interesting idea is, like as shown in this picture, is like you can do load to store for a single document, and this becomes very easy to write. Like your code to do that is very easy. You can make sure that you have like the proper HTML parser, you have the proper chunker, you're able to call your model to embed, and this like it trims the weeds out, right? You make sure that your code works with a single file, and then parallelization as a second concern, or like batching as a second concern, is it like its own task. Like if you were to like attribute points for a story or like tickets on development, if it works for a single document, you have like the second concern of parallelizing. And one like subtlety that we didn't highlight here is that, let's say loading, it takes a lot of IO time because you're doing like reading from file, for example, or you're calling a web request. You can have a parallel and collect just for load, and then you will have a list. And from this list, you can do things like you can later on like have other parallel collect. For example, like for the embedding, you might want to batch them. You can have a bunch of requests at once and send them to OpenAI or to your embedding model, so you can like expand and reduce where it matters the most. Because for like chunking or extracting, it's mostly CPU work. So having just the one branch per document makes sense, but maybe you want to send all your documents at once for embedding. I hope that was clear.
Yeah, that was clear. Yeah, that was great. Yeah.
Yeah, I guess
So it doesn't have to be at the end. The collect doesn't have
Yeah.
to be at the end. It can be anywhere. Okay,
You can
cool.
open and close at different points in the.
And I guess there's also a third potential architecture or another potential architecture that I haven't explored much, but it's an interesting idea where if you have some sort of buffer in the middle that's out of band that you're sending to a proxy that can collect requests and buffer up, then you can sort of slam it with that potentially and have that be it, and then have that, right, like have something that like takes your requests, groups them into a buffer, and then splits them back out. I haven't explored it, but it could be an interesting way to get it so that you can think about it in terms of individual items, but then have it get the efficiency of buffer and stuff. So, what do you think about it?
Yeah, I would say slightly advanced. So kudos if you managed to follow what they said. In terms of just to kind of round out this talk and this kind of deep dive, like I want to kind of talk about the kind of the caveats, right? Which kind of related somewhat, parallelization in scaling, right? And the thing that I kind of want to mention is that there's two dimensions to think about: domain specific and execution related. So parallelizing and scaling is definitely an execution related kind of thing, right? But I want to mention, so my experience is that you generally are going to be doing things that are domain specific. So you might have a cute demo. This is where it's LangChain, 3 lines. You can kind of do this. You're like, hey, I can do it. But like really, you're actually going to have to customize a lot more than what you can do in 3 lines of code. Hence why we see, pairing Hamilton with something like with LangChain you can start with, but then say we wanted to change how the text embeddings are done. We just have to change that one function. We don't have to change anything else in our pipeline, right? And it's just a function, and so we can use a bunch of things in it. So just to mention, you're going to be doing very domain-specific things. So for example, if you're doing PDFs, for example, right, classic cases, hey, the text is split across 2 pages. Right. Naively, if you just chunk by page, you might miss that, these 2 paragraphs are actually supposed to be linked together, and maybe they should be one. Right. And so just to mention that you're going to be doing, depending on your context, coming up and doing things that are, specific to your particular situation. And then from an execution perspective, right, you depending on your scale, not everyone has scale. Some people do have scale. Right, you are going to choose, parallelize or not, or just a for loop, depending on what your contexts are. Right. The one thing to kind of note is the scale and rapid pace of change. I wouldn't say, the lifespan of what you're doing is probably you're going to change or update the components or each one of these components more quickly than you probably otherwise would think, just because the field is moving so quickly. So new embedding models come out that are cheaper, better, faster, right? But that means you probably have to then tune a little bit more on like what the chunking strategy is, right? So you're going to have to change and change it. Say your project does well, now you have to ingest more documents, but those documents have different needs, and you have to extract text differently because you're trying to maybe they're different, or maybe what worked for 50% of them doesn't work for the others. So you're going to have to change and update your strategies as new things kind of come in. One thing that we assumed with this the current pipeline setup was that you're actually using APIs for things, right? So parallelizing APIs versus using GPUs are very different, right? And so actually, in the case of should you think about things in lists or not? I want to say if you're going to be running your own GPUs, you probably pays to think more in that kind of a way, because GPUs are data hungry, and you need to pass data in to it. So I have a link. If someone can link to the NER example, Thierry, if you can pull that from the LM workflows repo and kind of post it. But that shows an example of how you could write a pipeline that is focused more on batch, on like getting good performance out of a GPU using Hugging Face data sets. So rather than doing things in kind of by URL here, it does things as a data set. So in terms of links or other things, I think from a structuring code perspective, we have I want to say Hamilton and Burr are the 2 ways that we kind of obviously advocate for, slightly biased. But then in terms of extracting text, chunking text, there is many open source libraries, many different kind of tools you can kind of use. Similarly with embeddings, storage and indexing, likewise. And then if you need to scale stuff, I would think, Ray, PySpark, and Dask are two. Otherwise, we do have, if you are new to embeddings and want to know more about them, I highly recommend these two little kind of articles. One is more high level. Another one is a tech talk by Google, so very kind of more technically focused and oriented. So definitely, I want to say, if you're looking for things to plug in to build into, say, a Hamilton pipeline that's doing it, here's a bunch of links that can kind of help. And so to finish, thanks everyone for staying on and listening. So we basically walked through a little bit of high level what RAG is, and then specifically how dove into pre-processing documents and how you can model it as 5 discrete steps, and then showed you code in Hamilton of how you can kind of build a simple pipeline that does this. So any more questions on this? But otherwise, we did this in, I guess, just under 40 minutes, a little longer, but yeah. All right, cool. So we're not going to have a meetup in July because it's summer here in the Northern Hemisphere, so people are going to kind of be out, but excited to have Gilad talk about some of the stuff that him and Thierry kind of have been working on. So this is around kind of will be related to RAG stuff or something that you can apply to. So definitely you can think of it as how do you experiment with some of the input parameters, and how does Hamilton fit in and play a role, and that can kind of make that more manageable is roughly the high level gist of it at this stage. But otherwise, if anyone has anything to share, questions, etc., we can have an open mic. Otherwise, yeah, I will sit in silence for a couple of minutes in case anyone wants to pop up. Otherwise, thanks everyone for coming.
Thank you.
Yeah, it was a great session.
Thanks, folks.
Thank you, Stefan.
Sure.
All right, guys. I will call it then. Thanks, everyone. See you in August.
Cheers, folks.